Hello everyone, and welcome to the CSE116 Task 6 overview. Wow, it has been a long road to make it to Task 6. Task 1, 2, all the way up to 5, I think. It's been a lot of tasks, and they have not been easy. And it is truly a great accomplishment to have made it to this point. So of course I'm proud of all of you. And wait a second, I just checked 116 CSE116.com. This is the last task. That's it. After this task, there are no more deadlines for this class. So, wow, I mean, we're really at the end here. And as long as you guys have completed your quizzes, interviews, that means that you're pretty much done with the course. So that's crazy. Anyways, let's get into task 6 and start talking about it. Oh, geez, my eyes. That's blinding. Breath first search, BFS. What the heck? Graphs? What is breath first search? I mean, like, breath. Does that mean like breathing breath? What are we even searching for? Like, what is this? Well, hey, calm down. I'm here to clear some of this up for you. So clearly, you guys are probably like, what even is BFS? Probably have never even heard about it before. So that's where we're gonna get into some of it. I'm gonna move to the next slide. Oh, right. You guys already know how to do BFS because Jesse showed you guys in lecture. And I know that because I was there. Wow. So thankfully, Jesse has deeply went into how BFS works, and he's explained the whole algorithm, how to get from point A to point B in a graph. That's all explained in his lectures, and he has great slides posted. So, of course, I'm not gonna leave you guys completely stranded. Although BFS Jesse does he goes into a way better explanation than I could go into. It's very in depth and good. So if you guys didn't go to lecture for some reason, you're probably sick that day. Um, Please rewatch his lecture. It's super informative, and honestly, it'd be helpful if you haven't seen it to go watch it and then come back here because I'm gonna go more into how BFS slash how you could even get a graph. What is a graph? A graph from the game because I get that like you guys might understand the algorithm, but applying it to the game, that's a different story. So we're gonna talk about it a bit. So yeah, let's move on to the next thing about graphs. Oh, sorry, that's for a different class. All right, so snap, it's about time. We gotta have a talk. So it's a graph, right? Like we all, it's a classic. It's a bar graph, right? It's very informative. That's not a graph. At least not in computer science. That's not a graph. But this surely is. I mean, like it's there's x and a y, and no, that's not a graph either. Um, what is a graph then? I mean, like, no, surely that can't be a graph. It's just circles connected with like these lines in between. Like, that's oh my god, that's a graph. So, just like BFS, you guys probably barely even know what graphs are. So we're gonna talk about that a bit, and that's gonna get we're gonna go into depth there. But oh my goodness, that's right. Jesse also talked about graphs, and I was there, so I know that he did. So again, please watch Jesse's lectures, read his slides, because truly, it is a great resource before diving into this task. If you don't know what a graph is, you're going to have trouble. If you don't know what BFS is, you're going to have trouble. And don't solely rely on the video. Please go check out the slides and his lecture videos if you guys are confused, because it will totally clear up a lot of confusions. But again, um, obviously, it's hard to apply some of this stuff to the game, and so we are definitely going to talk about it here. So let's get into some of that. Okay, so here we have our game world that we're used to, of course. Like, we've seen this all the time. That's our game. Now, how do we translate this game into this graph-like structure? Because here we see this. This is from Jesse's slides, by the way. We see all these nodes that are connected by edges, and this is our graph. But like, we're supposed to generate that at runtime. Like every time we call our method that we're supposed to implement in this task. Because by the way, task is literally just one method. That's mostly what it is. Um, like upon that method being called, we have to generate this, and like, how do we do it? It's not that intuitive, like straight up. Like, sure, we might understand what a graph is and the BFS algorithm now, but I'm completely lost when I get to the game and have to code stuff. So let's talk about that a bit. So again, this is our graph. That's what you guys just saw. Now, here's the thing though. Each of these red circles, which you guys could probably deduct, they represent a location in the world, at least a location that's valid for us to go to. Okay, if you look at this graph for a second, you could probably determine that. Like, okay, yeah, like these circles are only on the grass and they're not touching the walls. So yeah, so for me, I'm gonna represent these circles as if every one of these red circles are vectors, and those are our locations for the different grid cells in the world. So I'm gonna pick a random one of these. So I'm picking this one right here. It's not related to the fact that this enemy's on it necessarily. Just that I'm picking this red circle right here for demonstration. So I picked this, and this is a vector 2D, and its location in the world is 9, 5. And you guys could verify that. Hopefully I'm right. Anyways, but this vector has 4 neighbors, and this is not new information. Like in the old pathfinding, we computed a path, the shortest path, but that path, of course, you would notice like this enemy up here would end up running into like this bottom wall or this left wall, and it wouldn't find its way around. We got a shortest path, but not a shortest path that avoided obstacles. So, that's the thing here. We're going to go back to the neighbor talk now. So this vector has 4 neighbors. We got 10, 5, which is this guy, 9, 4, which is this, 9, 6, which is this down here, and 8, 5, which is this guy. So there are at most from any vector on this grid, I can't find any that violates what I'm about to say. There are at most 4 neighbors for any of these vectors on the grid. So like if I were to pick any of these points, like this guy over here, I see 4 neighbors. We can verify that with these edges. This is a very nice graph for us to like visualize what we're about to make. So, okay, we establish a vector could have at most 4 neighbors in this graph that we want to make. Okay, now what about one that doesn't have 4 neighbors? So I'm going to look at this guy up here. Clearly we have 2 edges and not 4. So if we were to visualize this, this is a vector 2D at location 10, 2, and it has 2 neighbors this time, 10, 3. Wait, is that right? Yeah, 10, 3 and 9, 2. And the reason why it doesn't have a neighbor above it at 9, 1, no, 10, 1, and oh boy, I'm not even going to try this. But the reason why this is not a neighbor and why this is not a neighbor is because those are static game objects, and we don't want our enemies to pathfind into them. That's the whole point of this task. We want them to maneuver around them smartly. Smartly? Yeah. Anyways. Yeah, so we want them to be able to go around, so we have to not include them in the neighbors to our vector. Maybe. This is how I'm deciding to talk about this right now. So okay, we established that every vector in these red circles can have at most 4 neighbors. Sometimes we may not have a neighbor, such as like even this node right down here. We can tell it doesn't have one neighbor because there's a wall there. Sure. Okay. Now, this whole thing is it's a graph, and how we get this information is from adjacency lists. Now Jesse did talk about adjacency lists, but if you're completely clueless, an adjacency list maps, sorry, now I'm switching back and forth, but it maps a type to a list of that type. And in this scenario, we're mapping a vector to a list of vectors, which are the vectors that are adjacent to a vector. A lot of vector words and might be a little confusing, but if we're talking about adjacency, this is something to refer to. So vector 2D 9,5 in an adjacency list, this would map to its list of neighbors. Okay, vector 2D 9,5 would map to a list of vector 2Ds that would be its neighbors or the vectors that are adjacent to it, at least in the graph. And the reason why they're adjacent is because there's edges between them. And you guys are going to learn a lot more about graphs and like edges and all that stuff in like 250. So don't feel too overwhelmed if you're not fully getting it, but you need to get it at least enough to be able to compute BFS in this task. So yeah, this slide just clears some things up. This is me directly writing like what that hash map could look like, vector 2Ds to an array list of vector 2Ds. That's our adjacency list. And believe it or not, having an adjacency list represents all the data we need for a graph. Because we get every single point. If we think about it, we'll have every single red one of these dots, okay, which are, our vertices in our graph. And as long as we have an entry for every single one of these in our hash map, then we'll have all the data that this graph is visually showing us. As long as, say, this point right here, whatever it is, as long as this is in our hash map, then we know that we also have that this maps to its list of neighbors, or its adjacent vectors. And that's represented like more here. I talk a little bit about it. Yeah, it's useful because it helps us find the neighbors to any vector, which of course we need if we want to compute pathfinding. Because if we even did it with our eyes or whatever, I mean, this might not be the exact BFS path, but we'd go here and then like maybe from the player to the end goal or whatever. We'd start here, we'd go to this next spot, but then we realize we can't go here, so we go down. Just as humans, we naturally avoid the walls and we just maneuver around. But so yeah, the whole point about us doing BFS is to be able to avoid walls. Um, anyways, moving on. Oh, what? Um, oh my goodness, I totally forgot about this. Yes, you're right. This is kind of awkward because vector 2Ds are objects, so storing them in a hash map, like that kind of goes against stuff that we've learned so far. So, how do we accomplish that? How can we store vector 2Ds, which are objects, in a hash map and have it work as we want? The whole thing confuses me. No, 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 no. We're not doing this. I'm not a 250 TA. You guys are gonna learn a lot more about hash codes and how all this works in 250. But so we're gonna see in the doc in a second, or whenever I get to it. There are methods that you have to paste into the vector 2D class that define its hash code and dot equals. What that means? If you want to know more about it, I'd be glad to talk to you about it. A bunch of other TAs probably would, but you're going to learn it in 250. So don't worry too much if it's confusing to you because we don't expect you to actually know what those things do. But I will explain why it is useful to us, at least for this task. Just briefly, a little overview why it's useful. So take for example this adjacency list. Okay, I have some, it's like a sloppy representation of memory, but let's just say this is our adjacency list. We have two entries in, two vectors. In reality, this we'd have pretty much like the entire every all the entries for this adjacency list would be equivalent to the amount of red dots that we have here, because these red dots are the vertices in our graph. So yeah. Anyways, but just for this example and the small slide, I'm not putting all those on there. Let's say we have two vector 2Ds in our adjacency list, and they map to some list of vectors that are their neighbors, okay? As the definition of the adjacency list is. So we see here that we contain the vector 2, 2 in our hash map. And we see over here, we have two vectors. They have the same X and Y's, but they have different memory addresses. They're different objects. So in terms of memory, these are completely different things. Like they are in complete different spots on the heap. They are not equal to each other, especially not in terms of Java. If you were to compare them with dot equals, just before this change that you're going to paste into your vector class, they would never be equal. They're different references. But so say we called hash map adjacency list dot contains this guy. Okay, this vector 2D 0x200 up there. We'd expect that it would return true. Dot contains we see right here visually that that dot 200 or 0x200 is in this adjacency list. It's in our hash map. So naturally, we would expect to like, okay, if we did dot get with adjacency list dot get of 0x200, we would get back this 0x100 array list that denotes the neighbors to 0x200 in our graph. Now, with our hash code and equals change, we are actually able to get the same value from this completely different object on the heap. Now, the reason for this, to put it simply, is because when we are comparing these two vector objects now, we are not using their memory address or any other random information. We are using the x and y values of the vectors. They're pure actual data that we care about to say, okay, is this vector equal to that one? All that we care as the programmer, we are deciding that the only thing that matters between two vectors are that their x and y's are equal. Now, if you look at the code, it's a little different just to take care of some edge cases that could happen there. But all you guys need to know is that two different objects could map to the same thing as long as they contain the data that matters, which in our case is the x and y's of these vectors. So for simplicity, if I were to give this adjacency list, hey, adjacency list dot get 0x300, it would return me this value here, this 0x100, because in terms of Java now, after we implement those methods, this object, this vector 2D and this vector 2D are equivalent. Same with these two, of course, but those were with the memory address. But I get that it might be confusing, but all you need to know, and once you guys realize why this is useful in your task, you probably are close to scoring the point. But all you need to know is that you could get the same neighbors list if you don't have the exact object that you put in your initial adjacency list, as long as you have a vector of an equivalent value, which would be its x and y's. Okay? So take with that as you will. I get that that's slightly confusing, but if you try to work through BFS a little bit and you make your graph, you might realize why this is a useful property to you. Okay? Just take that for now. Now, all this being said, it's just still confusing. Like, how do you do it? How do you even make all this stuff just in code? Now, I can't. I just can't give all the answers. But what is useful to you specifically is the level.getStaticObjects method will return to you every single static object in the level, meaning all the walls, for example. And you know for a fact that these vectors, the locations that these static objects are invalid locations for our pathfinding. We saw something with invalid locations when we were looking at these neighbors here. This is invalid, this is invalid. We didn't include that in the neighbors for this entry in our adjacency list. Something to think about. But so, yeah, if I were to give some straight up steps, I would start by, in your method, you have to make a graph. So to make this graph, though, you have all the information that you need available to you from the level. Okay. Now, I get that it's a little bit unsatisfying for me just saying, like, look at the level.getStaticObjects, level.getBounds, I think is another one. But trust me, you guys can make a graph from this information, okay? Try it out a bit. And then after you have your graph, you run BFS from the enemy location to the players, kind of just like the old pathfinding. But BFS, though, is kind of the thing where I'm not going to describe how to do it because Jesse's slides go exactly how to do it. The thing is, the graph is the hard part. Probably. BFS is hard to implement, like, in code straight up, but Jesse goes over how to do that. Like, Jesse, his video, trust me, just go watch it. But the graph, translating the game to a graph, once you have a graph, though, like, once you have the structure in your game, or in your method, then like Jesse's BFS explanation applies to this graph. It applies to any graph. So it's easier for you to understand once you do the graph part first. So I would spend some time working on the graph before you get into like trying to make BFS. Make sure that the graph looks good. Use the debugger to ensure that your graph is like up to how you expect it to be. Make a test level. It's truly worth it, but it's the last test, guys. So really give it your all. You know, go to office hours if you need to. We're here to help. But yeah, wait, that's that's it. There's no more 116 after this task, but you guys might still want to make games. Like this was so fun making this game and making your whole game engine. Like this was awesome. So, um, if you guys are interested in making games just in general, I would personally love to welcome you guys to the UB Game Development Club. It's a great club. I'm there every Thursday. All these projects you're seeing on your screen right now are made from people that are in the club. Personally, I have 3 of mine on here. This one's mine, this one's mine, and this one's mine. You know, some of these like this one I made fully in the duration from when I was in the club, and this one. So, it's truly a great time. If you guys want to make more games or just talk games, you know, I'm there literally every Thursday. You guys can talk to me anytime. Um, please come. It's a great time. If you want to make more games, go to the club. But I gotta say congratulations to everybody because after this task, at least after this task, um, and after your interviews and your quizzes, you're done with 116. So that's literally it. I mean, like you guys you've been through so much, we've been through so much, of course, these videos. Um, but yeah, I got pretty much nothing else to say other than congratulations and good luck on your future courses. And I'll probably never see any of you ever again, right? I mean, nah, I'll probably see you guys more. But with that being said, I hope you guys have enjoyed these videos, and I think that's it. So I will see you guys later.